There we go. So this was a question that indicated that the answer to this quadratic equation, and let's not be thrown by the fact it's z rather than x, this quadratic equation has, and this is a classic case of maths pomposity, distinct, non-real, complex roots. Distinct means two. Non-real and complex, well, that's the same thing. That's completely superfluous. It's basically saying, until last Thursday, we would have said this equation has no solution. That's what they're saying. So if that equation has no solutions, what do I know is going to happen when I try and solve it with the formula? What's going to happen, Thurston, when I try?
The discriminant is going to be negative.
Right. So this question was just testing whether you could spot that all you needed to do was to say, right, if that's true, b squared minus 4ac is negative. And that was all really. In this equation, we had 1z squared, b was b, and c was 11. So b squared minus 4 times 1 times 11. And so the answer to the question is the solution to that. Now, we solved quadratic inequalities at GCSE, and you may remember me saying, always, always, always do a little sketch. Now, I'm sort of, this is b's, but I know if it was y equals x squared minus 44, it would be the y equals x squared curve that's been sort of pulled down to minus 44. So the key to know when is this less than 0 is to know these 2 points here, the roots. And our in the old days we would have had to, fiddle about. Our calculator will do that for us. And I know there's another way of doing it, but I like to use my calculator. So go on, just get your calculator and get it to solve that. So we've got a quadratic within a quadratic here, haven't we? There's a b squared term, so a is 1, but there's no b term, so b will be 0, c will be minus 44. So I've got 1b squared, no b's, and minus 44. And hopefully you know by now not to look up here, but to look here. And obviously it's going to be that, which is square root of 44 and minus square root of 44, because the other way of doing it would have been to say, I find this confusing though, because I'm thinking, right, if b squared has got to be less than 44, does that mean it's going to be more or less than the square root of 44? So I'd much rather do it this way with my equation. So this is square root of 44, which the calculator has already simplified for me to 2 root 11, so that's minus 2 root 11 and plus 2 root 11. We need to know when it's less than 0, so we're talking about the sandwich, and so that's why the solution is, well, of course that's not going to work, it's not working. B is between minus 2 root 11 and 2 root 11. So well done if you had a go at that and spotted it was a discriminant question. Well done if you weren't thrown by the fact there were z's and b's in there rather than sort of x's and y's. In these Active Teach textbooks, the E questions are the ones to go for. All right, we will be flying through this content as quickly as we can, and we'll focus on as many E questions as we can. Okay, so we're moving on today. Complex numbers, imaginary numbers, are a little bit like buses. They come along in pairs, don't they? So it is impossible, when you have a quadratic equation, to have one solution which is real and one solution which is imaginary. If it's going to have complex number, imaginary solutions, imaginary roots, there's going to be a pair. And more than that, it's going to be a plus bi and a minus bi. Okay, and we call those pair of answers complex conjugates, which again is yet another example of pompous math terms. It just means that when you solve a quadratic equation and there are no real solutions, you're always going to get a pair of imaginary, of complex solutions. So our solutions will always be in the form A plus or minus bi. So, you know, if it's 3 plus 2i, you're also going to get 3 minus 2i. You can't have one without the other. And there's a little bit of notation here. So let's say we call one of our solutions z. Its complex conjugate is referred to as z star. Don't ask me why. I have absolutely no idea. Just seems to be an opportunity to confuse you. Well, I lost my complex conjugate. I should be on page 6, that's right. Page 6. Okay, so here we've got a complex number, 2 minus 7i. So this question is just asking you to write down its complex conjugate, 2 plus 7i. But, you know, it's interesting what happens when you do that and what you do that. Remember that, you've got to grid it out, haven't you? So you've got to do one of the complex numbers multiplied by the other complex numbers. Just see what you get when you do that formula. When you add the two together, the pair together, and when you multiply the pair together. Sort of did that last time. Hopefully you've done a bit of practice of that. That term now, which is important. So we're keen really to get rid of the I bits when we're dealing with complex numbers. Yeah, that brings us back into the real world. Just like with surds, we're keen to get rid of our surd expressions. So it's interesting that when you take a complex conjugate pair and add them together, you do just that. You end up with a real number. And similarly, when you multiply a complex conjugate pair together, we already know, hopefully, that those disappear. And remember, I squared, well, the square root of minus 1 is I, so this is a really important result. I squared, therefore, is minus 1. So this actually becomes plus 49. So the answer there is 53. Both the sum of a complex conjugate pair and the product of a complex conjugate pair is a real number. It's a real number. Okay, where else have we seen not complex numbers, but something similar to this being used to make things a bit easier to deal with? How about if I show you the next example? Does this sort of ring a bell at all? Taking something which is a fraction and turning it into something that isn't a fraction? What are you thinking, Thurston?
So,
Yes, with surds. You remember with surds, if you've got, a denominator of 2 minus root 3, you multiply by 2. Excuse me, 2 plus root 3. Well, this question here is encouraging us to do the same. So what they want us to do here, to turn this into something which looks a bit less fractiony, is to take this fraction and multiply top and bottom by the complex conjugate pair of the bottom. So, and I'm allowed to do that. All I've done is multiply the top and the bottom of that fraction by the same thing. So just see what happens when you do that. This is not going to be a real number. This is still going to be a complex number, but we're happy about that. But this is z times z star, so we know that's going to be a proper number. Just have a go. I'm going to cross that out in a minute and replace it with something else. So I squared is minus 1, so that becomes minus 12. So my numerator becomes minus 2 plus 23i. And my denominator, well, I squared is minus 1, so that's going to become plus 9. So that is 13. And we mustn't think that A and B have to be integers, it doesn't say so, so I'm now going to divide both of those things by 13, so I've got minus 2 over 13 plus 23 over 13. Have I done that right? Does anyone else agree with me? That's right. That's right.
Yeah, I agree.
Yes, Rory?
Would you not get the mark if you didn't do that last step?
If it asked for this, you would not get the mark, no. So you've always got to be careful that you give it in the answer. It would probably say where A and B are rational numbers, rational meaning fractions. Yeah, sure. That you're looking on the phone, is it? So,
No, it's.
things to
I
do.
said I'm not on the bus, but.
Things to do. Okay, now let's just look at one before we move on, and I'm going to give you some practice of this to try independently. But before we move on, let's look at just one question from the chapter that follows, which is question 11. So I'm we're into the E questions here. So z is a complex number. So z is going to be an a plus bi number. It's not a constant, it's a complex number. And we want to know what z is. So what we basically want to do is we want to end up with an expression that says z equals. It would seem to me to make sense, therefore, to start by getting an expression that says z minus 2i equals. And to do that, we just need to divide both sides by that. At which point I hope you'd say, oh, hang on a minute, this is a complex conjugate pair answer. I'm going to multiply top and bottom by the conjugate partner of that. Go on, see what you get. See if you can get an answer. Z, remember, is a complex number, so it's going to be a plus bi. It's going to be just like in the previous question, a complex number. But this is going to tell us what z minus 2i is. So we just would then need to add 2i to get what z is. And z, as I said, is a complex number. I guess I sort of hope that at this point you multiply by 20 because, you know, that's because I've taught you that we hate fractions. It's probably not the easiest way of doing it in this case. It's probably easier to write that as 4/5 minus whatever, but I'm going to still stick with multiplying by 20 because I hate fractions. So multiply by 20. And I want z on its own, so I'll get 20z on its own by adding 40i, so that's 16 plus 12i. Then I'm going to divide by 20. 16 over 20 is 4/5, and 12 over 20 is 3/5. Just going to double check I've got that right. Wrong question. Well, what do you know? If you've managed to, while I think of it, if you've managed to get access to ActiveTeach, the core Pure textbook through ActiveTeach, by far the best way, because you get the solution banks built in. So that button there, which you should find by each exercise, doesn't just give you the answers, it gives you their work solutions. Now, of course, there's always the danger that they do it a slightly different way to me, but I hope that's far more helpful, and that works with your other textbooks as well. So I would encourage you to do that. So some example questions there, fairly basic. You may feel you can skip that. I'd like to go through that one on Thursday, and that one's again the deeper you get into the exercise, the tougher it gets. So that's quite a challenging one. So let's apply this complex conjugate thing sort of in reverse. Rather than me giving you a quadratic equation and saying solve it, here's a question where you're given one of the solutions to a quadratic equation and it's a complex number. So you've got to write down the value of the other solution, the other root. Hopefully that's nice and easy because we know they come along in pairs like buses. And then multiply it out to find what the original equation was. And then we're calling the two roots alpha and beta, so that's just like we did a moment ago with z and z star. What do you get when you add those two roots and multiply those two roots together? Just have a very quick go at that. So we know that if 7 plus 2i is one of the solutions to a quadratic equation, 7 minus 2i will be the other one. That's the starting point, isn't it? So if we have an equation where the solutions are 2 and 3, we know it looks like that when you factorise it. So in this case, we've got an equation where the solutions are 7 plus 2i and 7 minus 2i. So we get this rather ugly looking factorisation. And that becomes x minus 7 minus 2i. And that becomes x minus 7 plus 2i. We're now going to multiply that out. I'm always going to put my i's at the end. It doesn't really matter, but now, to sort this out, I'm going to deal with the things that have got an x squared in them first. That's nice and easy. I'm then going to deal with the things that have got an x in them. So the things that have got an x in them are here and here, which cancel out, and here and here. So that is minus 14x. And then I'm going to look at the things that are not, that haven't got x's in. So that's these things, four things here. Those cancel out. So I get plus 53, and it's a quadratic equation. So that's equal to 0. Have I got that right? Anyone agree?
Yeah, that's
There's a relief. There's a relief. Good stuff. And then if you did the two roots added together, then that would have given you a real number, 14 in this case. And if you multiplied the two roots together, we know, I mean, they didn't use the grid, I like the grid, that we get 53. We'd already sort of done that in the process of working this out. So I had an example question from that. So page 9, 3 and 4, and then a bit of a doozy, page 10, question 7. That's my second little block. And you know, I say again, I haven't got the capacity, I'm afraid, to sort of check up on you. You know, so this is entirely up to you, how you do with it, how you do it. Okay, let's now move on to something new and exciting. You'll notice that a lot of the stuff you're going to be asked to do with complex numbers is nothing to do with quadratics. Occasionally it comes back into quadratics, but a lot of the time it's just manipulating. And you know, and a lot of when we get to practice papers, which we will do, you'll see a lot of the complex number questions are just sort of manipulating type questions. Right, but now let's talk about cubics. So we've said that when you have a quadratic equation, you either have two nice real solutions, b squared minus 4ac is positive, one solution, otherwise known as repeated solution, b squared minus 4ac is 0, or two imaginary or complex solutions, which are a complex conjugate pair, and that's if the discriminant is negative. Right, what about if we've got a cubic? Now we know that cubics, at their very basic level, the cubic looks y equals x cubed, looks like this. But the general form of a cubic is going to look like that or flipped around. So there are potentially three roots, three solutions to the question, where does this cubic, and sorry, I should explain what I mean by cubic. That's an equation where the highest power of x, or whatever the variable is cubed. There are three solutions, potentially, three solutions. And so when you've got a cubic, you can factorize it into three separate factors, and those factors will give you three separate solutions. And this is the bit I wanted to show you. So for a cubic equation, either all three of these are normal numbers, or you get one normal number and two imaginary numbers, and guess what? The two imaginary numbers are a complex conjugate pair. Okay? That is provided that the equation has three roots. So, you know, you've got cubics which only have one root. You've got cubics which have two roots. But the vast majority of x cubed expressions have three roots, three places where they equal 0. And if we are dealing with one of those, we've either get three real, normal, nice numbers, or we get one real number and a complex conjugate pair. There's no other solution. You can't have three complex numbers. You can't have three complex number solutions. It's impossible. You can't have two real numbers and one complex number. Complex numbers always come in pairs, just like the good old bus. And so this allows me, oh dear, is anyone on the period 6 bus? People going on the period 6 bus? Right, and who's catching it up? Just if I overrun a little bit, what time does your bus go on?
Oh, it would go at 20 to 6.
Oh, right. So, yeah, we're not going to stay till 26, don't worry. Right, okay, so here we go. -1 is a root of this equation. So this equation, and they're using z, annoys me a little bit, but there we go, has minus 1 as a solution. And remember, what we're asking here, what we're saying is that these are solutions to when does this equal 0? When does that equal 0? So go on then, Rory, what do I know goes in the bracket?
Maybe z minus.
Oh, sorry, yes, with z, aren't we? If z minus 1 is a solution, what's going to go in the...
Oh, z plus 1.
Z plus 1, that's right, yeah, z plus 1. Now, we don't know at the moment whether these two roots are real or whether they are imaginary. But I do know that if I multiply those two out, I'm going to get a quadratic, aren't I? And so at this point, we do a little bit of detective work. Firstly, I want to know what k is. And in order to know what k is, I use the fact that z equals minus 1 is a solution. Remember, that means that the answer, one of the answers to when does this equal 0 is minus 1. So what does that mean I can do to work out what k is? One of the answers to the question, when does this equal 0, is minus 1. What can I do?
Just plug in minus 1.
If I plug minus 1 in, I know that the answer will have to be 0, and that will allow me to work out k. Go on, do that bit for me first. I'm going to start off by making z equal to minus 1, and we use this notation for it, for that. F of minus 1, we used that when we did functions at GCSE. So I know that f of minus 1, making z equal minus 1 in that expression, will come out as 0. What's k in, Jack? 5. Yeah, k is 5. Yep. So we got that k is 5. Now I'm hoping, therefore, that you can quite easily tell me what A and C are. Now we know that that has to be 5. These two multiplied together need to give me that. So I'm hoping that without a huge amount of effort, you can tell me what A and C are. What's your interest in? Can you tell me what A would have to be, so that when I gridded this out, I got this is the answer?
Isn't H1?
A is 1, yeah, because we've just got 1 z cubed, so A is just going to be 1. That's nice and easy, isn't it? And Frank, what would C have to be, so that this multiplied out would give me 5, yeah. We just need to work out what B is now, and for that, I am going to do a little bit of gridding out, but I'm probably not going to do the whole thing. I know that I need 3 z's, so it might be that I can get away with just multiplying it out to get the bits that are going to give me a z term. I know that I need 3 z's, so I know that when I multiply this out, the number of z's is going to be 3. So see if you can work out what, remember we're just trying to work out what B is. Any suggestions? What do you reckon, Ben? What's B got to be?
-2.
It's got to be -2, hasn't it? It's got to be -2. Can we just spare 2 more minutes just to finish this off? So B's got to be -2. Now I have to say, I rushed that fast and I want. What we're after are the other 2 roots. So what we now just need to do is reach for our calculator and solve that quadratic equation. So if you just do that for me quickly. So not the whole cubic equation, and it's interesting, you are allowed to use your calculator to solve quadratics, you're not allowed to use your calculator to solve cubics. So what we're doing is we are whacking in this equation. We can always check the answer, but and if you've got your calculator set into complex mode, you should get 1 + 2i and 1 - 2i. So they told us one root, which allowed us to get one factor, and we were then able to work out what the other 2 factors multiplied together would be, and then we could solve it. And this is a really key technique, and it's a nice technique, and there's more than one way of doing it. So what I'm going to do is, I didn't get as far as I hoped, so if I suggest that we, if I add this question to the list, so this is page, is that page 13 or page 8? It's page 12, page 12. And question 1. The only reason I just want to show it to you now, they're telling you that f of 2 is 0. So what they're telling you is that 2 is a solution. Okay? 2 is a solution. And therefore, in this example, your first bracket is going to have -2 in it. And hence, solve this completely is exactly the same thing. We solved that first one completely. So page 12, question 1, just have a go at that one, and then I'll show you the other way of working that out. There's a second way of doing it, which is a bit less sort of detective. Sorry to everyone. We'll leave it there. We'll see you Thursday. I am very, very happy.